In this video, we're looking at how to make a buffer and how to make a good one. So the first step to making your own buffer is to making it an effective buffer. To be an effective buffer, we need large and equal amounts of our acid and our base. The base being the proton acceptor and the acid being the proton donor. We need large amounts because that's going to increase our capacity of our buffer. The more of our acid and base we have within our buffer, the more that it's able to neutralize. We also want to have equal amounts of our weak acid and its conjugate base, or vice versa. Whenever we have equal amounts of our weak acid and conjugate base, that Ka expression, if A- and H3O plus are equal to each other, Ka is just equal to H3O plus. So the best buffers have H3O plus equal to Ka. If we take the negative log of both sides, that means the best buffers have pH equal to pKa. And that's a very important thing to remember. Good buffers are going to have large equal amounts. Whenever we have those equal amounts, pH equals pKa. We can also see that pH equals pKa is true when looking at the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, we have pH equals pKa plus the log of that base over acid concentration. Well, again, if our base over acid concentration are equal, this ratio is equal to 1, and the log of 1 is equal to 0. So we still end up with that pH equals pKa. So let's look at an example problem here where we're trying to figure out how to make the best buffer. So this industrial process wants a buffer with a constant pH of 3, or it requires a constant pH of 3. They're going to do that using a buffer. These are the weak acids that are available, and we're given the Ka values for each. So first we want to know which of the 4 acids would be the best choice. Explain with a calculation. Well, we just learned that best buffer has pH equal to pKa of the acid that's in it. Well, we want a pH of 3. We need to find our acid that has the pKa closest to 3. In our pKa values, we're going to take the negative log of all of these given Ka values for our different acids. When we look at those different pKa values, we see that nitrous acid is closest to that constant pH that's required of 3. Remember estimating those pH values? We can do the same thing with our pKa's. So if we take a look at our exponents here, if we want a pH close to 3, it's probably going to be the 2 or the 4 one. So we didn't necessarily have to calculate those others if we knew they would be further away from looking at that exponent. Well, we figured out which of our acids would be the best choice. We need to go ahead and explain why our nitrous acid is the best choice. So we know HNO2 was the best choice because the pH of that buffer system is 3.14. We know that because pH equals pKa. However, we must be specific when that is true. pH is only equal to pKa whenever you have equal concentrations of your acid and your base. So we need to be sure that we are in fact stating that. So our nitrous acid is the best choice because when our acid concentration is equal to our base concentration, the pH of the buffer solution is 3.14 molar. Well, why is that important? Because that's the closest to the desired pH of 3. We did need to justify this or explain it with the calculation, so we can just go ahead and add in and show our pKa calculation as well. And again, since that pKa is closest to our desired pH, that's what's going to be our best buffer. Looking at part B here, we need more than just our weak acid to make the buffer. we want to give at least one possible chemical that could be used here. Well, buffers, what are they made out of again? Buffers are made out of a weak acid and it's salt. So we need a salt that contains the conjugate base of our nitrous acid. Well, the conjugate base of nitrous acid is that nitrite ion. It also has to be a soluble salt. So maybe sodium, that's pretty common. Sodium nitrate. Sodium nitrite, my apologies. Okay, so again, buffer is made out of weak acid and it's salt. The salt comes from the conjugate base of it. So the conjugate base of nitrous acid is nitrite. So we need to add a soluble nitrite salt. Pick something that's soluble with nitrite. Sodium's the easiest thing that we can pick here. Okay, so lastly, part C. We want to know how much of that soluble salt that we picked in chemical B we need to achieve a buffer with a pH of 3. Well, our buffer is going to have a pH of 3.14 when our concentrations are equal. But if we vary the concentrations of our acid and our base, we can make the pH of our buffer equal to exactly 3. Well, anytime we're looking at pH of buffers mathematically, we're going to go to that Henderson-Hasselbalch equation. That tells us that pH is equal to pKa plus the log of our base concentration of our acid. Our base is that nitrite ion, and the acid is our nitrous acid that we've plugged in there. Well, I want the pH of my buffer to be 3. I know it's pKa. We already solved for that in part A. It was 3.14. Well, again, as we said, if these two concentrations are equal, the pH of our buffer is equal to the pKa of 3.14. We don't want that. We want the pH of 3, so we need to figure out what ratio that we need here. So we're going to go and solve for this ratio. Got a little squeezed in down here, but 0.14 is equal to the log of our base to acid ratio. To cancel out that log, we're going to have to take 10 raised to the side of both. Raised to the power, of both sides. It's going to cancel out our log. So 10 to the 0.14 power is going to equal that ratio. So that's 0.72. Well, we want to know how much of our chemical of part B. Well, the chemical from part B is that NO2 minus ion, so that's our 0.72. We need 0.72 moles of that NO2 minus ion per every 1 mole of our nitrous acid that we use within our buffer. So let's think about if that makes sense. We want a buffer with a pH of 3. Whenever our concentrations of our acid and base are equal, is 3.14. We want our pH to be a little bit lower than that. Lower pH means that we're more acidic. Well, if we look at our ratio here, we have more acid than base because we have 1 mole per 0.72 moles. So that more acid than base is going to make our pH of our buffer system just a little bit more acidic than our pH equals pKa equal amount scenario. All right, so let's continue on with our buffers. First off, we have this little multiple choice question here. We want a buffer solution with a pH of 5 and want to know which acid would be the best choice. But this is multiple choice, no calculator. Go ahead and take a moment and see if you can figure that out using your pH estimation skills. It's going to work the exact same way with pKa since they're both the negative log. So again, take a moment, try that out, resume the video when you're ready to see the answer. So we should have gotten C here. That Ka value we can estimate, remember we're estimating to the nearest factor of 10, so we can estimate that to 1 times 10 to the negative 5th power, which means the negative log of 1 times 10 to the negative 5 is going to be 5. If we take a look at the rest of these, this is going to be closer to a pKa of 8 because of that exponent there. If we look up here, that's going to be more like 10 times 10 to the negative 2, which is 1 times 10 to the negative 1. So that's a pKa of about 1. That's not very close either. Here we have 10 times 10 to the negative 3, which is what it would round to, which would be 1 times 10 to the negative 2. So a pKa about 2. That's not very close to 5 either. So we could do all of them or just see, oh, hey, this is 5. That must be the pH of 5, especially when this 1.8 is rounding to 1. All right, so there's more ways to make a buffer. Making a buffer part 2. We can make a buffer from a weak acid or base by reacting it with something strong. So let's talk about that. We're going to take our strong base, NaOH, and add it to the weak acid, HA here. Well, we know when acids and base react together, they neutralize each other. So if I added 1 mole of my weak acid and 1 mole of my sodium hydroxide, we're at that perfect stoichiometric ratio. We're going to have a complete neutralization reaction where we're only making the salt and water. But if we only have half the amount of strong base as our weak acid, only half of the weak acid is neutralized. Let's take a look at that. I kind of write out a little BCA table in here, kind of with that line in the middle, but that's okay. If we started with 1 mole of HA and we only add half the amount of sodium hydroxide, which is 0.5 molar, sodium hydroxide's limiting. So since it's limiting, all of it's going to react and we end up with no sodium hydroxide left over. But since we have a 1-to-1 mole ratio, only half of our weak acid reacted, half of it remains. But we also made some products. We made half a mole of water and half a mole of sodium A. Well, that sodium A contains A minus. That's our conjugate base of our weak acid HA. So if we only added half the amount of strong base to our given amount of weak acid, after that reaction, we have weak acid and its conjugate floating around in water. Well, that's what a buffer is, a weak acid with its conjugate base. Anytime you have a titration reaction where you have a weak acid or weak base titrated with something strong, you're going to have a buffer after that first drop of your strong titrant is added. We're going to learn more about titrations and how that relates to our buffers later, but for now, super important to understand what's happening here. So let's go and look at some more examples of this. We have lots of different ways we can make a buffer, as we've seen. If you're mixing a weak acid and base with something that's strong to make a buffer, we have to make sure we're not completely neutralizing our species. So we're gonna have to look at the different mole amounts that we have here. So looking at example number 1, we have, well, in all these examples, we have acetic acid with sodium hydroxide. Well, example number 1 says it's a buffer. Let's check out why. First off, on all of these, we have a weak acid, acetic acid, that we're mixing with a strong base. Given the correct ratios, that always has the potential to make a buffer. But for that acetic acid, we have 20 millimoles, 100 times 0.2 molar, and for sodium hydroxide, we have 10 millimoles. Well, we're only adding half as much strong base, which means we'll neutralize half of our weak acid into its conjugate base. That leaves us a mixture of weak acid, conjugate base. So yes, that's a buffer. If we look at example number 2, we have 20 millimoles, 100 times 0.2, and 10 millimoles, 50 times 0.2 again. So we're only adding half as much strong base compared to weak acid. Again, that's a buffer. In the third example, we have 20 millimoles of each. That's not going to be a buffer. Our strong base completely neutralized our weak acid. The only thing that's going to remain is a salt and water. No weak acid. Buffer has to be weak acid plus the salt. All our weak acid's gone. The NaOH neutralized it all. Okay, last example here. Looking at this last example, oh, we changed our acid. This is nitric acid now. Nitric acid's a strong acid. Sodium hydroxide's a strong base. That's not a buffer. Strong acids and bases don't make buffer. It has to be a weak acid or a weak base with its salt. So we're going to go through and see what else we can identify as a buffer here. And all these different combinations and neutralization reactions going to occur. We need to know what products we're going to make. Are we going to end up with a weak acid and salt? And compare how much of our stuff is present. So I would start by looking to see what we have. When we look at this first one, we have HCl. That's a strong acid. NaOH is a strong base. Well, strong acids and bases don't make buffers. That's not going to be a buffer. And the second one, going down this column here, we have a weak acid, strong base. Well, combined in the correct ratios, something weak with something strong can make a buffer. So let's see if we have the correct ratio here. We have 100 times 1, so 100 millimoles of our weak acid. And we also have 100 millimoles of our strong base. Well, we can only add half as much as our strong base. Here we're adding equal amounts. They're going to completely neutralize each other. That's not a buffer. There'll be no more weak acid left over. All right, looking at the next one, we have sodium acetate. Well, that's a salt. But salts can be acidic, basic, or neutral as well. That sodium ion came from sodium hydroxide, strong base. Acetate came from acetic acid, which is a weak acid. Strong one wins, so this must be a basic salt. And HCl is a strong acid that we're mixing that with. So we have a weak base in our basic salt with a strong acid. So this can be a possible buffer. Let's look at the amounts that we're adding. We have 100 millimoles of our weak base. 100 times 50, we only have 50 millimoles of our strong acid. So we're adding half as much strong acid. That'll neutralize half of our weak base into its conjugate. We end up with both weak base and conjugate. So guess what? This guy can be a buffer. Take a moment and pause the video and go through these last 3. Figure out which, if any of these, or multiple ones of these, can make a buffer. Resume when you're ready to check. So you should have found that that middle one is the only one going to make the buffer. The first one is strong acid, strong base. Those don't make buffers. Second one, we have weak acid, strong base. So if we look at our ratio, we can see, we're only adding 50 millimoles of strong base. That's half as much as weak acid. We'll neutralize half of it. Acid and conjugate will be left over. Last one, we have weak acid, strong base again. So we're on a roll, but we had 50 millimoles of each. That's going to completely neutralize that weak acid. All right, so those are 2 different ways to make a buffer. And to round this all out and get some more practice on our buffers, we're going to finish with this free response problem. A lot of this we have seen problems similar, so what I want you to do is pause the video, take a few minutes, see which parts you can get through. We're going to go through the whole thing here in just a sec. After you've paused the video and tried it out on your own, resume when you're ready to go through and check each part. Maybe you do the first couple parts, check it, pause again, do the next few. Regardless, try this out on your own a bit. All right, so pause again, resume when you're ready to check. So we want a buffer at pH of 4.30. we have this following list of acids. First thing we want to know is what weak acid would work best. So again, pH equals pKa in our best buffers. So we need to look at the pKa for all of our weak acids here. So using my exponents, I only ended up calculating the pKa for these two, since I know from estimation those would be the ones closest to our pH of 4.30. To find that pKa of 4.19 from our benzoic acid. That's closest to 4.30. That's going to be our best choice. Now we just need to go and justify that. So we know that the best buffers have pH equals pKa, but again, make sure you mention that's only true when acid concentration is equal to our base concentration. So let's show that pKa calculation to prove this. That pKa calculation gives us the pKa of 4.19. That's closer to 4.30 than any other available acids, again, making this the best weak acid choice. On part B, you needed to identify an appropriate salt. Well, buffers are made out of the weak acid and its salt. We got to pick a soluble salt, so let's just put sodium with our conjugate base. So that salt that we put with our weak acid must contain its conjugate base, which would be that benzoate ion, and it has to be soluble, so we just stuck benzoate with sodium. Moving on to look at part C, we want to write the equilibrium reaction for this buffer. We've seen that a few times as well. Writing the reaction to describe a buffer system, we always want to start with our weak acid. We're going to take the acid part of our buffer, react it with water, act as acids to donate a proton, form the H3O plus and our conjugate base. We know we got a buffer because we got weak acid and conjugate base, it's salt. Looking at part D, we want to know what would have to be true about that acid to base ratio in our buffer solution if we prepare our 4.30 buffer. Well, pH equals pKa when that ratio is 1. Well, that would be 4.19. That was our pKa. We want a pH of 4.30. That's a little bit more basic, so our ratio is going to have a little bit more base in it. But we can use Henderson-Hasselbalch to actually go and calculate this. As we do that algebra, we find that our ratio is equal to 10 to the 0.11 power, which means that we would have 1.28 moles of our conjugate base per every 1 mole of our benzoic acid. Well, again, that makes sense. That pH we wanted was a little bit more basic than when we have an equal ratio, so we're going to need a little bit more base in our buffer. We got 2 more parts to talk about. Let's look at E. We want to know how would adding HBr to the buffer change that ratio. Well, HBr would be adding a strong acid. So let's see what strong acids do when we react them. Strong acid, really we're only adding the H plus part. The Br minus would just be a spectator. Acids react with bases, so we need the base part of our buffer. The base part of our buffer is that benzoic acid, the benzoate ion. And since we're adding something strong that's going to get completely neutralized by that benzoate ion, we're going to end up forming our benzoic acid. That's the other part of our buffer here. So whenever we form that, we're going to be making more benzoic acid and we'll have less benzoate ion. So that is going to change our ratio. So as we saw in our reaction, adding that strong acid reacted with the conjugate base part of our buffer. That ratio would decrease as our conjugate base concentration decreases and we make more acid. One last part here. How else could we prepare this buffer solution from our weak acid if we were not given the salt, but instead concentrations of strong acids and strong bases. Well, here we just learned about that. We can add a strong base is what we would need to our weak acid, but we can only add half as much, so we only neutralize half of it. So adding strong base to our weak acid until our moles of strong base equals half the moles of our weak acid. That's going to neutralize half of our acid into its conjugate base, leaving weak acid and conjugate base in solution. That's exactly what a buffer is. The last important thing to note here, that strong acid is not useful at all. You can just ignore it. We're going to be working some more with buffers in class, possibly making one and seeing how they work, but there you have a start on all the fun buffer things we need to know.